Welcome, welcome, warm welcome. Get your pencil, pen, whatever it is you write with. Get a notebook. You're here for math from the void. Math coming at you out of nowhere. Today we have a problem from the 1997 UP Calculus BC exam. A bit of a doozy on this one. We have this kind of implicit differentiation set up. Very interesting. So let's get into it. It starts off saying that we just have to show that this point is on the graph, which is nice. It's saying as long as k is greater than 0 because we need the k to be positive. Otherwise, you can't do the square root. So all we have to do is plug this in and make sure it works. So we have to make sure that 4 equals k times the square root of 2 over k squared plus 2. Well, the square root of 2 over k, right, squared is just going to be 2 over k. So this is going to cancel the square root, and then the k is going to cancel the k. So we're just going to have 2 plus 2. And 4 equals 4, so therefore it's true. No matter what the k value is, as long as it's positive, this point, 4 comma square root of 2 over k, will be on the graph. Okay, not bad. Part B, show that the tangent line, so we need to use something with the tangent line at that point, 4 comma square root 2 over k. We want to make sure it passes through the origin. So what does that mean for it to pass through the origin? That means that when x equals 0, then the y equals 0 as well. But we have to use the tangent line to plug in the 0 and check. So that means we need the equation of tangent line. When you see equation of tangent line, you need to write this down. Y minus y value equals m, which is the slope, times x minus x value. Now the slope, even though we were given an x equals a function of y type equation, the m, the slope, is still dy dx. Still the rise over the run. The dx over dy would not give us the rise over the run. Okay, so let's take a look at the dy dx. We need to use implicit differentiation here. We get that x equals ky squared plus 2. So if we take a derivative of both sides, we just get that 1 equals 2ky dy dx from the chain rule. And therefore dy dx equals 1 over 2ky. There we go. Well, we need to find the slope at a particular point. What point? At the point 4 comma square root of 2 over k, which means we can use this y value, square root of 2 over k. So we're going to say this is 1 over 2k times the square root of 2 over k. So this gets a little bit complicated, but one way to think about this is if we flip it, we'll have square root of k over 2 square root of 2 k. And this will simply be 1 over 2 square root of 2k. That is the slope. Okay, I know that looks funky, but that is the slope at the given point. So let's write our equation of tangent line now. It's going to be y minus square root of 2 over k equals the slope 1 over 2 square root of 2k. Oh, and sorry, the k needs to be in a root as well. Times x minus 4, because that's the x value for this point. So let's check if by some miracle, if we plug in x equals 0, this works out somehow. So if x equals 0, then we say y equals 1 over 2 root 2k times 0 minus 4. Kind of promising. That's negative 4 plus square root of 2 over square root of k. I'll write it like this. So this is going to give us negative 4 over 2 square root of 2k plus square root of 2 over square root of k. So what I can do is I can make these the same denominator by multiplying the top and bottom by 2 square root 2. And if I do that, I get negative 4 plus root 2 times root 2 makes 2, and then times the other 2. So that's going to be 4 over 2 square root of 2k, which, look at that. That equals 0, as long as k is not 0. And so our y value is 0 when x equals 0. That means the origin does pass through. Or I should say the tangent line does pass through the origin, right? So we used the tangent line here. We tried to plug in x equals 0 because we want to make sure that this tangent line is going to pass through y equals 0. And it does. All right, now let's move on to part C. Part C says let R be the region in the first quadrant bounded by the x-axis. It's in the first quadrant, okay? So if you don't know what this graph looks like, it's going to be a rightward-facing parabola, something kind of like this. But we only want the portion in the first quadrant. Oh, and it's plus 2. So it's shifted by 2. So it's something kind of like that. But it's also bounded by this x-axis, and it's also bounded by x equals 4, which is like right here. We want to write an integral expression for the area, but we also want to show that the area is decreasing when k is increasing. So we want some kind of inverse relationship between the area, which is this area, and if k were a different value. So if k were a different value, the shape of this graph might be like more wide. It just kind of depends, or it might be more narrow. It could be something like that. It could be very narrow. And if that's the case, this has less area. So what k controls is k kind of controls this stretch factor, which gives the logic behind why the area would decrease as k increases. But we have to like show an integral expression for this. So right now we have an x equals. We don't want that. We want the top portion of this, which is the square root graph. Let's solve for y. We get x minus 2 equals k times y squared. So x minus 2 over k equals y squared. And then we would solve this by saying plus or minus, but we want the plus portion only. We don't want this bottom minus portion. Okay, so this is going to be y equals the square root of x minus 2 over k. And if you'd like, we can call this 1 over square root k times the square root of x minus 2. I think that's just a little bit nicer. So this is the equation of the graph that we're looking at, and we want to find the area inside of there from 2 to 4. Let's write this in the form of an integral. Area is the integral from x equals 2 to x equals 4 of 1 over root k, which is just a constant. It's just some number. We don't know what k is, but it's some number. Times, let's call it x minus 2 to the 1/2 power. Okay, pretty straightforward. Let's go ahead and do the antiderivative here. So that's going to be 1 over root k. X minus 2 raised to the power by 1, so that's 3/2 power. Divide by the power. Dividing by a fraction means you multiply it by the reciprocal instead. And this is going to be evaluated from 2 to 4. Okay, so we're going to have 2 over 3 root k times 4 to the 4 minus 2 to the 3/2 power. So that's just 2 to the 3/2 power minus 2 minus 2, so that's 0 to the 3/2 power. So here we have 2 times the square root of 2, but it's cubed, so it's times itself 3 times. It's going to give us 2 root 2 over 3 root k. And as you can see, these numbers up here, they're important because that's part of the integral, but you'll mostly notice that this shows us the inverse proportionality. As k gets bigger, the area, this fraction, gets smaller. That's what we're saying. As k goes to infinity, the area goes to 0. I guess I should be more precise and say as k as it approaches infinity. I was going to say as k approaches 4, but that's not necessarily true. K can be any number, any positive number. So that shows that the area decreases as k increases. All right, this is a pretty fun problem. This said BC, but I think it's approachable by somebody in an AB class. They just have to be familiar with implicit differentiation, and then they have to realize that little trick at the end, that to express this, since it's bound by the x-axis, you actually want to integrate dx, which means that you're going to want to have like some kind of function y equals f of x in your integrand. That's enough for me today. See you next time in the void.